Your Linux machine is running fine. Everything feels smooth. You have a browser open, a few terminals, maybe a database or a development server humming in the background. Then, without any warning, without any countdown, without any mercy, something disappears. A process you needed, a tab that was doing work, a server that was handling real traffic, gone, just gone. And somewhere deep inside your kernel logs, buried in a wall of text, is one cold, quiet line that explains everything. Out of memory, killed process. That line is not a bug. That line is not a mistake. That line is your operating system making a choice. And the terrifying part is, it made that choice without asking you, without warning you. It calculated a score for every single running process on your machine, found the one it decided was most expendable, and sent it a signal it could not survive. The Linux OOM Killer had spoken, and it almost never kills what you want it to kill. This is the story of one of Linux's most misunderstood, most feared, and most fixable problems. And by the end of this video, you will understand exactly what is happening inside your kernel when memory runs out. All why the OOM Killer picks the victims it picks, and most importantly, how to set up your swap correctly in 2026 so that the OOM Killer either never fires or fires at exactly the right target. Let us start at the very beginning, because you cannot fix something you do not understand. Your computer has physical RAM. That is your fast, expensive, limited memory. When you open an application, it loads into RAM. When you run a query, the result lives in RAM. When your browser opens a new tab, that tab's data goes into RAM. RAM is fast because it is directly connected to your CPU. Accessing data in RAM takes nanoseconds. That number matters because everything else is slower by comparison. A fast NVMe SSD takes microseconds. A spinning hard drive takes milliseconds. RAM is roughly 10 to 30 times faster than even the best solid-state storage. That speed gap is why your system wants to keep everything in RAM and why it fights hard to avoid going anywhere else. But RAM is finite. It has a ceiling, and modern software pushes against that ceiling constantly. So what does Linux do when RAM fills up? This is where most people think the system immediately starts crashing or swapping, but that is not what happens. Linux has a layered defense system, and it exhausts every option before it reaches for its last resort. The first thing Linux does when memory gets tight is look at something called the page cache. The page cache is a massive portion of your RAM that Linux uses to hold file data it has recently read from disk. If you read a configuration file, Linux keeps a copy of it in RAM in case you need it again. If your database reads a row from disk, Linux caches that block in RAM. The page cache can consume gigabytes of your RAM on an active system, and that is completely intentional. Linux does this because reads from RAM are instant and reads from disk are painful. The genius move is that Linux treats that page cache as evictable memory. The moment something more important needs that RAM, Linux drops those cached pages without mercy. No data loss, no drama. The original data is still on disk, the cache just vanishes and makes room. So the first line of defense against memory pressure is simply reclaiming page cache. On a system with 16 gigabytes of RAM, Linux might have 8 or 10 gigabytes sitting in cache that it can reclaim in milliseconds. This is why your Linux system often reports very little free memory but runs perfectly fine. That cached memory is not wasted. It is working, and it is ready to be surrendered the instant something more important needs the space. But what happens when the page cache is gone? When real applications are consuming memory faster than Linux can reclaim it? When every last byte of RAM is genuinely spoken for? This is when Linux turns to swap. Swap is disk space that Linux treats as an overflow zone for RAM. When RAM fills up and the page cache is exhausted, Linux takes the least recently used pages from RAM, compresses them or moves them to the swap space on disk, and frees up that RAM for whatever needs it right now. Later, if a process tries to access data that was swapped out, Linux loads it back from disk into RAM. This is called a page fault, and it costs time. That time is why swap is slow, not because Linux is doing anything wrong, but because you're now doing RAM speed work at disk speed. The physics are against you. For decades, the guidance on Linux swap was simple. Make your swap twice the size of your RAM. That advice came from an era when RAM was measured in megabytes and disk was the only overflow option. It stuck around long after it stopped making sense. Today, that old rule will actually make your crashes worse, not better. Here is why. If you have a 16 gigabyte RAM machine and you follow the old rule and create 32 gigabytes of swap, you have given Linux an enormous amount of room to push pages to disk before the OOM Killer ever wakes up. That sounds like a good thing. But what actually happens is that your system slowly sinks into swap hell. Every page that gets pushed to disk is a page that costs microseconds or milliseconds to retrieve. As more and more active data ends up on disk instead of in RAM, your system starts thrashing. Thrashing is the term for when your machine spends more time moving data between RAM and disk than it does actually doing work. Your CPUs are busy. Your disk is screaming. But nothing useful is getting done. The system becomes completely unresponsive. And ironically, the OOM Killer, which would have quickly killed one process and let the system breathe, never fires because there is still technically swap space available. So instead of one clean death, you get a slow agony that lasts until you force a reboot. This is the paradox at the heart of swap sizing. Too little swap and the OOM Killer fires fast and sometimes kills the wrong thing. Too much swap and the system dies slowly without ever getting relief. The modern recommendation for most desktop and server workloads is to size swap much more conservatively. The current guidance from system administrators and kernel experts in 2025 and 2026 is to use swap as a genuine safety net, not as a second RAM pool. For systems with 8 GB of RAM, a swap of 4 to 8 GB is typically enough. For systems with 16 GB, 4 to 8 GB of swap is still a reasonable ceiling, not 16. For systems with 32 GB of RAM or more, even 4 GB of swap can be sufficient, because the real goal is not to extend your usable memory, it is to give the kernel just enough breathing room to react before everything locks up. But swap size is only one piece of the puzzle. The more important piece is a kernel parameter called vm.swappiness. Swappiness is a number between 0 and 200 on modern kernels, though most systems still use the traditional 0 to 100 scale in practice. The default value on most Linux distributions is 60. This number controls how aggressively the kernel prefers to push anonymous memory pages to swap versus how aggressively it reclaims page cache. A higher swappiness value means the kernel starts using swap earlier, even when there is still free RAM available, prioritizing keeping the page cache warm. A lower swappiness value means the kernel clings to RAM longer before touching swap at all. For desktop users, the almost universally recommended swappiness in 2025 and 2026 is 10. At a value of 10, your system will only start swapping when it is genuinely under memory pressure, not because it is being cautious or preemptive. This means your applications stay in RAM longer, your system stays responsive longer, and swap only appears when you actually need it. To set this right now, you open a terminal and type sudo syscall w vm swappiness -10. To make it survive a reboot, you add vm swappiness -10 to your sysktl.conf file and run sudo syscall p to apply it. That single change alone will make a noticeable difference in how your desktop feels under load. For servers, swappiness recommendations vary more widely. If you are running a database server like MySQL or PostgreSQL, a swappiness of 1 is common. Database engines are extremely sensitive to latency spikes, and even a brief moment of swap activity can cascade into query timeouts and connection failures. At swappiness 1, the kernel virtually never touches swap unless it is truly an emergency. If you are running a general-purpose server with mixed workloads, swappiness of 10 to 30 is a solid range. Now let us talk about the thing that every Linux user in 2026 should know about, but most still do not. There are better ways to handle swap than writing pages directly to a disk file or partition. They are called zswap and zRAM, and understanding the difference between them is genuinely important. Zwap is a kernel feature that sits between your running applications and your disk-based swap. When the kernel decides a memory page should be swapped out, instead of immediately writing that page to disk, zswap intercepts it, compresses it using an algorithm like LZ4, and stores it in a small compressed memory pool inside your RAM. Your disk-based swap file is still there as a backup, but as long as the compressed page fits in the zswap pool, it never needs to go to disk at all. Later, when the page is needed again, zswap decompresses it from that pool and hands it back in nanoseconds instead of microseconds. You get the benefit of freeing up RAM without paying the disk I/O penalty. The trade-off is a small amount of CPU time for compression, but on any modern processor, that cost is trivial compared to the alternative. Zwap is now enabled by default on several major distributions. Arch Linux enables it by default. Ubuntu has been moving toward it. The default compression algorithm in recent kernels is LZ4, which is excellent. LZ4 compresses at speeds of several gigabytes per second and decompresses even faster. In practice, typical swap pages compress to roughly half their original size, which means you can fit twice as much data in the zswap pool compared to uncompressed swap. To check if zswap is active on your system, you run cat sys module and just swap parameters enabled. If the output is Y, it is running. You can also check the pool size with cat just sys kernel debug swap pool total size. The default pool size for ZSwap is 20% of your total RAM. You can raise this to 25% by adding zswap.max-pool%25 to your kernel command line or sysctl configuration. zRAM works differently. Instead of sitting in front of your disk swap like zswap does, zRAM creates a compressed block device entirely inside your RAM. You can format this device as swap, and when the kernel uses it, pages go into this compressed RAM device directly with no disk involvement at all. zRAM pages live and die entirely in RAM. They are faster to access than swap because there's no disk fallback path at all. The compression ratios are similar, typically 2:1 or better, but zRAM has a hard ceiling. Once the zRAM device is full and you have no disk swap behind it, the OOM Killer fires immediately. There is no overflow. The practical difference in 2025 and 2026 is this. zRAM is the better choice for systems where swap usage is predictable and moderate, where you want the absolute fastest swap response time, and where you are comfortable with a harder memory limit. Zwap is the better choice for systems where swap usage is variable or heavy, where you have a fast NVMe drive that makes disk spill tolerable, and where you want a genuine safety net below the compressed pool. For most modern desktops with 16 gigabytes of RAM or more and an NVMe drive, swap backed by a small swap file is the cleanest solution. For systems with 8 gigabytes or less, zRAM configured at 50% of RAM is often the winner because it gives you the fastest possible response during memory pressure on a system that is already tight. You should never run zRAM and zswap simultaneously. The Arch Linux wiki specifically warns against this. They conflict at the kernel level, and combining them produces unpredictable behavior. Now let us talk about the OOM Killer itself, because even with perfect swap configuration, there will be moments when memory genuinely runs out. And when that happens, you need to understand how the kernel chooses its victim so you can influence that choice. Every running process on your Linux system has a number attached to it called an OOM score. This number lives at processiding karn OOM score. You can read it for any process by substituting that process's actual ID. The OOM score is calculated by the kernel using several factors. The most important factor is how much memory the process is using. A process consuming 4 gigabytes of RAM gets a much higher score than one consuming 200 megabytes. A higher OOM score means the kernel is more willing to kill this process when it needs to act. Lower OOM score means the process is relatively protected. The kernel also factors in how long the process has been running. Newer processes score higher than older ones because a long-running process is more likely to be something important, like a database that has been serving requests for days. Root-owned processes and processes with certain administrative capabilities score lower, meaning they are somewhat harder to kill. But these protections are not guarantees. A root process that is consuming huge amounts of memory can still get a high OOM score and die. There's also a second file called OOM_AGG at proc process ID OOM_ADG. This one you can write to. The range is -1000 to +1000. Writing -1000 to this file tells the kernel to never kill this process under any circumstances. Writing +1000 tells the kernel to kill this process first, before anyone else. Writing 0 leaves the default behavior intact. To protect a critical process, for example, a database with a process ID of 5432, you would run echo 900 hardware sudo t proc 5432 or OOM score ADJ. The -900 does not guarantee survival, but it makes this process far less likely to be chosen compared to everything else. If you want something protected permanently across restarts, you add this to the service's system unit file with the line OOM score adjust 900 inside the service block. System supports this natively, and it applies the setting automatically every time the process starts. For containerized workloads in 2026, the OOM Killer behaves somewhat differently. In systems using cgroup v2, which is now the default on most modern distributions, including Ubuntu 22.04 and later, Fedora 31 and later, and Arch Linux, each process group has its own memory limits. When a C group hits its memory .max limit, the OOM Killer fires within that C group, killing the most memory-hungry process inside that group, not necessarily the most memory-hungry process on the entire system. This is enormously useful for Kubernetes clusters and Docker environments because it contains the damage. One misbehaving container cannot take down the entire node. In 2026, the gold standard monitoring tool for memory pressure in production Linux systems is PSI, which stands for Pressure Stall Information. PSI was introduced in kernel version 4.20 and has matured significantly. You access it by reading a proc pressure memory on a system-wide level. The output shows you, in real time, what percentage of time the system is spending stalled waiting for memory. A number above 5 to 10% for the full metric is a serious warning sign. It means every non-idle task on your system is waiting for memory to become available. That is the precursor to a crash, not the crash itself. PSI lets you build alerts that fire before the OOM killer does, giving your monitoring stack the ability to react by evicting containers, scaling down workloads, or spinning up additional resources before the kernel starts making decisions for you. Now, let us walk through a complete practical setup for a Linux desktop with 16 gigabytes of RAM in 2026. This is the configuration that keeps your system stable, fast, and protected. First, check what swap you currently have with the command free h. Look at the swap line. If it shows 0, you have no swap, and you need to add some. If it shows a massive number like 32 gigabytes, you likely have the old double RAM configuration and should resize it. To create a new 8 gigabyte swap file, run these commands in order. First, sudo fallocate, L8G, swap file. If your file system does not support fallocate, use this alternative instead. Sudo ddd if dev0 of swap file bs1m count 8192. Then set the permissions. Sudo chmod 600 swap file. Then format it as swap, sudo mkswap swap file. Then activate it, sudo swapon swap file. Then verify it is working. Swappin show. To make it permanent across reboots, add this line to your etc fstab file, swap file, nunswap, sw00. Next, set your swappiness to 10. Run echo vm swappiness, star10, sudo t, a etc sysctl.conf. Then apply it immediately without rebooting, sudo sysctl, pa. Now check if swap is enabled. Run cat sys module z swap parameters enabled. If it shows Y, you are already benefiting from compressed swap caching. If it shows N, you can enable it by adding the swap. Enabled 1 to your kernel boot parameters in your bootloader configuration file. While you are in sysctl.conf, there is another parameter worth setting. It is called vm.vfs or part cache pressure, and it controls how aggressively the kernel reclaims memory used for directory and inode caching. The default is 100. Setting it to 50 tells the kernel to be more conservative about reclaiming this cache, which improves file system navigation speed under memory pressure. Add this line, vmvfs cache pressure /50. Run sudo systl, p again, done. To verify the OOM score of your most important processes, run the following for any process ID you care about. Cat myproc PID OOM score. For a database like PostgreSQL, find its PID with pgrep postgres, then read its score with cat proc that PID OOM score. If the number seems high, protect it in the system service file with OOM score adjust 900 as described earlier. To watch for OOM events that have already happened on your system, run dmesg t grep I killed process. This searches the kernel ring buffer for any logged OOM kills with human readable timestamps. If you see entries here, your system has been silently killing processes, possibly for days or weeks, without you knowing. Many mysterious application crashes that look like bugs are actually the OOM killer doing its job quietly. For systems running containers with Docker or Podman, always set memory limits on your containers. Without a memory limit, a single container with a memory leak can consume all available RAM and trigger a system-wide OOM event that kills unrelated services. You set a container's memory limit with the flag. Memory does 512 lemurs when you start the container. Docker and Podman will then enforce that limit using CE group v2, and if the container exceeds it, only processes inside that container are at risk, not your entire system. Let us talk about one mistake that is extremely common in 2026 and becomes more dangerous every year as RAM prices stay elevated. The mistake is disabling swap entirely on systems that run out of it and crash, under the assumption that removing swap will force better behavior. This sounds logical. If the problem is that the system is using swap and crashing, removing swap prevents it from using swap. Problem solved, right? Wrong. Completely wrong. Without any swap, the OOM killer activates at a much lower threshold. There is no buffer, no breathing room. The moment RAM fills up with no cache to reclaim, the OOM killer fires immediately. And on a system without swap, it fires at the absolute worst time, because the system has no recovery path. At least with swap, there is a small window where the system can offload inactive pages, give a process time to release memory voluntarily, and allow normal operations to wind down gracefully. Red Hat, the company behind one of the most widely deployed enterprise Linux distributions in the world, explicitly states that systems without swap can make sense in specific scenarios, but that in most environments, a small amount of swap is the right choice. Their guidance is to keep swap available and use score-adj to protect the processes that matter. There's also a parameter you should know about called vm.overcommit top memory. The default value on most Linux systems is 0, which means the kernel uses a heuristic to decide how much memory to allow processes to allocate beyond what is physically available. The kernel is allowed to say yes to a memory allocation request, even if it does not have the physical RAM to back it immediately, because in practice, many allocations are never fully used. This is called overcommitting. It is why you can launch 100 small processes that each request 1 gigabyte of RAM without actually having 100 gigabytes available. The kernel bets that they will not all actually use their full allocation at once. When that bet is wrong, the OOM killer pays the debt. Setting vm.overcommit memory to 2 disables overcommitting entirely. The kernel will only allow allocations that it can fully guarantee from physical RAM plus swap. This is more conservative and means some allocations will fail immediately at the point of request, with an error your application can handle. Many database administrators prefer this mode because it is more predictable. A controlled failure at allocation time is better than a mysterious death hours later when the overcommit debt comes due. Setting vm.overcommitMemory to 1 means the kernel always says yes to any allocation, no matter how large. This is almost never the right choice for a production system. It maximizes the chance of a devastating OOM event because the kernel has made promises it has absolutely no ability to keep. For most users in 2026, leaving VM overcommit to memory at 0 is correct. The default heuristic is well tuned for general workloads. If you are running a dedicated database server, vm.overcommit pass memory 2 paired with a carefully tuned vm.overcommit ratio is worth investigating. The overcommit ratio controls what percentage of RAM plus swap the kernel considers as its total guarantee pool when overcommit is set to 2. Let us take a step back and look at where the Linux kernel stands in 2026 with respect to OOM handling specifically, because there have been meaningful improvements in recent years. Modern kernels in the 6.6 to 6.14 range, which are the kernels that ship in or power major distributions right now, have refined the OOM scoring algorithm specifically for high core count systems. The post 6.6 fixes improve accuracy when dozens or hundreds of threads are competing for memory simultaneously, which was a scenario where the older OOM heuristic sometimes made poor choices. If you are running a kernel that is older than 6.6 on a system with 16 or more CPU cores and heavy parallel workloads, upgrading your kernel is itself a meaningful memory management improvement. The PSI pressure monitoring system, while available since kernel 4.t, has also become significantly more reliable and granular in recent kernel releases. The per-C group pressure data is now stable enough that production monitoring systems at major cloud providers use it as their primary signal for automated scaling decisions. Facebook, now Meta, was one of the early adopters and has used PSI across their server fleet for years. Their engineering blog has documented how PSI lets them catch memory pressure events that would have been invisible to traditional metrics like memory usage percentage or swap usage. The practical takeaway is that in 2026, you should be reading trigger proc pressure per memory on any Linux system you care about. Set up alerting if the full percentage exceeds 5 to 10 over a 60-second window. That alert will warn you before anything crashes. It is the closest thing to a check engine light for your kernel's memory management, and most monitoring setups do not use it yet. Here's one final thing that will make everything we have discussed click into place. The OOM killer is not your enemy. It is actually the feature that keeps Linux alive under conditions that would force a complete freeze or a kernel panic on other operating systems. A system that kills one process and keeps running is better than a system that freezes solid and loses all work across every process simultaneously. The OOM killer exists because the alternative is worse. The question is never whether the OOM killer should exist. The question is whether it fires at all, and if it fires, whether it kills the right thing. The answer to the first question is proper swap sizing and the right swappiness value. Small swap, swappiness at 10 to swap enabled. That combination gives the kernel a tool to use before the OOM killer wakes up, and it prevents the slow thrashing death that kills responsiveness without ever triggering recovery. The answer to the second question is OOM_ADG. Know which processes on your system are critical, protect them with negative values. Consider leaving disposable worker processes or browsers with neutral or positive scores, so the kernel's choice, if it comes to that, falls on something you can afford to lose. And the answer to catching problems before they become crises is PSI monitoring. Read pressure memory. Build alerts around the full metric. Treat rising memory pressure the way you treat rising CPU temperature, as a signal that demands action before it becomes a failure. Your Linux system has one of the most sophisticated memory management systems ever built into an operating system. The page cache, the reclaim logic, the swap layers, ZSwap, zRAM, the OOM scoring algorithm, PSI pressure stall tracking, C group V2 isolation. All of these layers exist because the engineers behind the Linux kernel spent decades solving the hardest problems in computer science at the most fundamental level. The OOM Killer is the last line of that defense. It is blunt, it is final, and it is honest. When it fires, it is telling you something true. Your system ran out of memory. And now it is fixing that the only way it can. Your job is to configure everything above it so well that it almost never has to. Set Swappiness to 10. Size your swap conservatively. Enable zSwap. Protect your critical processes with OOM Score ADJ. Monitor memory pressure with PSI before the crisis arrives. Do those 5 things, and the OOM Killer will go from the silent killer quietly crashing your system to the emergency backup it was always designed to be. That is how you win the memory management game on Linux in 2026.